Now, for the benefit of all our audience who joined today, welcome you all for this Thursday webinar series, jointly hosted by Kairos Kinetic and Global Biomedical Research Foundation. Today, we have our esteemed speaker, Dr. Anupma Thakur, who is Postdoctoral Research Associate at Purdue School of Engineering and Technology, Indiana University, Purdue University, Indianapolis, Indiana, USA. Today's title of the webinar is Nano-Engineered Materials for Sustainable Energy and Smart Sensing, Opportunities and Challenges. Before we go to the webinar, I would take few minutes to introduce our speaker, Dr. Anupma Thakur. I met her on Twitter. I follow her on Twitter, and I requested her on Twitter that she be our webinar speaker, and she kindly accepted our invitation. Thank you so much, Dr. Anupma. She's currently the Postdoctoral Research Associate funded by National Science Foundation and Department of Energy at Purdue School of Engineering and Technology at Indiana University. And she's also an early career research fellow at IIT Gandhinagar, Gujarat, India. She completed her PhD as a DST Inspire Research Fellow at CSIO, Chandigarh, India, August 2021. She earned a gold medal in Masters of Technology as well as Bachelors of Technology. And she is a well-established young nanotechnologist in the field of advanced nanomaterials and material science for various applications, including materials for clean hydrogen energy generation, carbon capture and utilization, chemical sensors, photoelectrocatalysis, extreme environment, and actuators. Dr. Anupma has published more than 34 international high-impact publications, filed 5 patents, written 12 book chapters, presented more than 20 conference papers. I see her updates in Twitter regularly, and also delivered more than 60 oral talks. She also attained more than 850 citations to her published research contributions. Her research interests include 2D materials, nanomaterial synthesis, smart sensors and actuators, energy harvesting and conversion devices, green hydrogen production, carbon dioxide reduction reaction, environment pollutant monitoring devices, and degradations. She's also honored with many awards, including Young Engineer Award 2022 in Metallurgical and Material Engineering from the Institution of Engineers India, Technologist of the Year 2022 Award from the Institute of Electronics and Electrical Engineers, Distinguished Alumni Award 2022 from Punjab University, Chandigarh, Best PhD Thesis Award 2022 from IIT Kanpur, BRICS Young Scientist Award, Russia Conclave 2020, India Synthesis Award 2020 from Anupma, India, National Academic Excellence at Indo Global Education Summit from Government of India 2013. This is only a brief introduction. It's my pleasure to read such an illustrious career for such an young and dynamic woman scientist. Thank you so much for being with us today on this webinar, Dr. Anupma. Now the forum is yours. We welcome you once again.
Yes, thank you, Dr. Shri, for the kind invitation and kind introduction. And it's my pleasure to be speaking at this, global platform. So without any delays, I would like to share my screen. Please. And start over the talk. So just confirm me when my screen is visible.
Yes, it is visible. You can move to slide share. Yes, perfect.
Yeah, okay. So thank you for having me, and greetings to everyone who is present in witnessing the presentation. So just sharing my brief research avenues that I have been exploring in terms of sustainable energy and smart sensing. So as a young nanotechnologist, I have been working on synthesizing materials and, having some functionalities over them to find their suitable applications in terms of energy and sensing. So a few research canvas and some opportunities and some challenges that we have been facing, and definitely young generations who are contributing to these fields can lead to new advancements. So going ahead, and just trying to talk about briefly about nanotechnology, which is a new frontier in terms of science and engineering. So a few couple of slides for, just an introduction. So as we know, right, the famous quote by Richard Feynman, the father of nanotechnology, which talks about there's a plenty of room at the bottom. So just trying to understand it with a small example, that if we see a 10 centimeter region in our skin, if we go deeper and deeper, we see what is the scale of a smallness that we are talking when we talk about nanotechnology. So considering 10 centimeter of your skin, area, and going more deeper into 1 centimeter, then further to 1 millimeter, and finally reaching to 100 microns, and further reaching to 10 microns, which is composed of white blood cells, going further deeper to 1 micron, and further to 100 nanometers, and reaching the scale of DNA. So with this, degree of smallness that we are considering when we talk about nanomaterials or nanotechnology is this regime. So this regime is very important for material scientists and, young engineers to understand that the scale that we are talking is about the plenty of, space, the plenty of skillness that we are talking about at the degree of, ranging from 1 to 100 nanometers. So this is just brief example of a human hand, how, what is the degree of smallness. So considering this example, now we talk about the arena of materials and the scale of nanotechnology that, we need to consider when we are contributing to this field. So understanding nanotechnology in terms of, science and engineering. So it is basically the field of science and engineering which talks about working with materials at a nanoscale. And the definition of a nanomaterial or nanoscale refers to how 1 to 100 nanometers. So you can imagine a a thin sheet of paper, which is about 100,000 times nanometers thick. So that is the degree of smallness we are talking. If we talk about human hair, so it's about 80,000 to 100 nanometers, in wide, or is the degree of smallness. So contributing to this field, we talk about having an interdisciplinary focused area. So if we look into how nanotechnology connects disciplines, so we talk about having inputs from science and engineering, the AI models that are coming up, the machine learning that is helping us to understand the new avenues in materials. We talk about electrical engineers, which can be contributing towards designing small transistors, small electrical devices. We talk about biomedical biology, as you all are contributing and trying to explore the field of nanotechnology by designing biomarkers, nanosensors, nanobots that can reach even the blood streams and even dedicated cell organs. So with all that, we talk about material scientists, which are focusing in planning to investigate new materials with functional applications. We talk about chemists, which are working in exploring new molecules. Physicists and mechanical engineers, we are talking about designing a small resonator. So with all these examples, we just need to understand that this is an interdisciplinary field, and every engineer or scientist is directly or indirectly trying to get into nanotechnology to explore recent advancements. So with this, it is a field where all disciplines meet, and this is where we need to collaborate with each other to find a sustainable solutions for future. So with this understanding, now as we know, like when we talk about nanotechnology, it's all about, talking about nanomaterials, by talking about their functional properties, how they can be produced, what is the scale, and what is the I would say the characterization, the categorization of nanomaterials in terms of dimensionality. So we know there are many, naturally occurring nanomaterials. There are human origin that are incidentally made nanomaterials, and there are engineered nanomaterials. So as we know, right, the focus of my presentation is on nanoengineering of materials. So wherein we design materials with tunable properties that are being used for specific applications. So we talk about engineering, how we can synthesize these materials, how we can use them. And we also talk about the classification of materials in terms of dimensionality. So nanomaterials, as I said, 1 to 100 nanometers of the space of nanomaterials is further divided based on their dimensions. Either it can be a zero-dimensional material, which has its all three dimensions in nanoscale, and are generally the small nanoparticles or quantum dots. If you work on one-dimensional nanomaterial, so you're working upon the material which has its two dimensions in nanoscale, and one is in microscale. So we talk about generally nanorods, nanowires, and even fibers, and even nanotubes. So when you're working on two-dimensional materials, specifically you're working on material which has its one dimension nanoscale and the other can be in microscale. So the best example that I have for you is my current material that I'm working on, which is a nanosheet and is also known as maxenes or M-beans, depending upon what materials you're using to synthesize those materials. And then comes 3D materials, which is basically a bulk material, which does not have any dimension in nanoscale and is often considered as a bulk, 3D counterpart, which is used to synthesize these materials. So based on these dimensionalities, we can understand that the arena of working on nanomaterials is vast. And each one of you, if you have interest in nanoengineering, can largely contribute to designing new materials with functional properties. So with this understanding now, we look into the diverse applications, starting from biomedical research to healthcare, environmental protection, energy, and even agricultural mechanical engineering. So this is the leading edge which has been rapidly developing for science and engineering, and large efforts by young generation are needed to contribute to this field, to have large impact. So with this understanding, now we talk about nanoengineering for energy applications, which is my primary focused area in which I have been largely contributing to designing nanomaterials for solar energy harvesting and, electrocatalytic or photocatalytic conversions. So with this perspective, before jumping to that aspect, I briefly want to take your attention towards why we are talking about energy transition. So as we all know that, we are depending on large fossil fuels, and with a rise in the world population, the energy demand is increasing. So to cater that demand, we need some alternate energy fuels which can fulfill the energy demand, basically. So to go through that, we need to plan ahead and think into having alternate fuels. So one aspect is to have renewable energy, which is vastly growing in a couple of years and will take us to, deal with this energy transition. But we still need some additional fuels which can, complement with the renewable energy and contribute to fulfilling the energy demands. So we need to have our focus towards clean energy fuels or sustainable fuels, which can help us to maintain the environmental sustainability and also they cater the needs of growing world population. So that is one aspect. Now we also look into the sustainability of our planet. So we have per capita CO2 emissions, which are huge contributions based on the dependence that we have today on fossil fuels. So we see that if the global map itself, portrays that there is a huge CO2 emissions, which is contributing to the, I would say, non-sustainability of planet Earth. So to understand this, we need to have sustainable fuel, which can take care of our mother planet Earth and does not release, huge CO2 emissions to the environment, causing damage to the, sustainability. So understanding these two perspectives, we talk about drivers of clean energy economy. So the prime, focus is towards renewable energy that we all know, and solar energy being the, abundant source of renewable power is being investigated and, largely explored for designing clean energy technologies. So here, the other solution that, my research focuses on is to use the solar energy and convert it into a chemical fuel. So that is where my most of the doctoral and postdoctoral research experience aligns to, and we are working on harvesting this solar energy by artificial photosynthesis, designing electrodes which can largely harvest the solar energy and convert it into electrical chemical fuel, which is a hydrogen. So that's what we are proposing as a green hydrogen. And further, the green hydrogen can be used as a feed to fuel cells. And further, we can get electrical energy to drive the energy economy. So based on this, briefly touching upon why hydrogen. So as we know, the hydrogen is basically the high energy content and clean fuel based upon its, the energy density. We talk about hydrogen because of its geological abundance, which is the third most common element on Earth's surface. And also, if we talk about the sources of hydrogen from where we can get it, so the primary source is water. We have fossil fuels, we also have biomass. But a large focus is on utilizing water as a fuel because water as a precursor for synthesizing hydrogen is more suitable because and we also talk about clean energy as hydrogen, right? So when we produce hydrogen from water, it end up into water as a byproduct. So it's a clean energy economy with zero carbon emission. So this is the cycle of renewable hydrogen in which most of my research is focused on. So we take water, we take solar energy, we design electrodes which which harvest solar energy and participate in chemical reactions and further reduce water to produce hydrogen. And we collect that hydrogen and further use it for various applications. So this is the hydrogen economy chain, which is presented on my screen, which talks about its production to application. So starting from production based on the photo electrochemical water splitting that I'll be discussing in my coming slide, and further collecting hydrogen and using for the delivery, we use generally cryogenic tanks, pipelines, and cylinders. As we know, hydrogen storage is critical. So we have sophisticated cylinders and technologies which can help us to store hydrogen and further, use it as a compressed liquid fuel and further use conversion technologies like the best one today is the fuel cells. And finally, transport, stationary and portable electronics, and even electrical grids are the prominent application where we can use the produced hydrogen. So this is the whole chain of clean future fuel that I'll be discussing in my presentation. So now, before we jump into hydrogen and focus on its various aspects. So it's very important for me to discuss with all of you that we talk about hydrogen, but we need to understand that there is a color palette for hydrogen. So when I'm saying green hydrogen, so basically I'm touching upon the technologies which use green processes to produce this hydrogen based on renewable energy or renewable source of light, which is the feed for the process. But there are other pellets of hydrogen which are currently available and are contributing to carbon emissions. So that's what we want to distinguish green hydrogen technology with other pellets of hydrogen. So just touching briefly upon the gray hydrogen, which is basically the product in which fossil fuel or coal or methane is used as a source. And the process is coal gasification or SMR gasification. So with all these technologies, we convert coal into hydrogen and with the abundant release of CO2 into the environment. So that's again is not a green process. Then we have blue hydrogen, which is again the feed remains methane or coal. However, the process is again the coal gasification with some carbon capture. So with this, we are able to control, the CO2 emissions, which are going out of the, process chambers. But again, it can only capture 85 to 95%. So still we have that we release some CO2 into the environment. Then comes turquoise hydrogen, which is again using methane or a, carbon-based source, and pyrolysis is the process. And again, it results in CO2 emissions. So with all these technologies which are already existing in the application domain, generally turn over into large production of hydrogen with these processes with huge CO2 emissions. So this is where we want to propose green hydrogen technology to cater the demands of hydrogen, which is being produced around 94% with all these established technologies. But as we know, these all are contributing to huge CO2 emissions. So we need to replace them with the green hydrogen technologies. So with this understanding, now we move ahead and talk about more about, energy transition, the bigger picture. So as I mentioned, like we are into energy transition, we need to understand by what time domain we will be able to actually reach to the point where we have a sustainable goals. to fulfill those goals. So we consider, like, as stated by ARENA report, by 2050 we can see renewable energy hitting the market with large technologies catering to energy. So with these goals, if we look into the focused domain, so in terms of renewable energy share, also we see solar energy impacting largely the renewable energy map. So with this contribution coming from solar energy, the practice or the technology that we have in green hydrogen production can also largely contribute to this field. So with this, now we need to understand, like, when we are working in energy, we're talking about affordable and clean energy, sustainable goal. And with this, if you talk about contributions made to the country, so we working on this domain as largely talking about promoting innovative ecosystem for affordable, renewable, and clean energy solutions. So with that focus, if you talk about how the technique works, so just going more deeper into the technical details of the project. So we talk about designing electrodes. Now, what those electrodes will do is basically solar energy harvesting. So before going that, we need to understand the annual solar energy radiation. So if you look into the geographical, positions of India in the global map, so we have abundant solar radiation reaching the surface. So we need to design technologies which can harvest the abundant solar energy. So the establishing technologies which are existing today are like, solar cells, we have silicon solar cells, multi-junction solar cells, and other technologies. So with all these technologies, we are basically trying to harvest solar energy and convert it into electrical energy as an output. So similarly, we have a competitive technology that is photoelectrochemical cells, which I'll be discussing in the coming slide. But before that, just talking about the hydrogen today, the share of hydrogen. So I would say the partners or the key applications where hydrogen is being used is industry. So if you talk about chemical industry, refining industry, iron and steel, and even the general industry, so we look into the numbers. So it's about 65% of hydrogen which is needed is by chemical industry. We have about 25%, which is basically is needed by the refining industry. So to fulfill all these demands, we need a technology which can produce hydrogen with sustainability. So with all that, we need processes. So we have green hydrogen, which can fulfill these gaps, the demands of chemical and renewable, I would say, refining industry. So to meet those demands, we need a transition in the green, in the hydrogen production, I would say. So when we talk about hydrogen as an energy carrier, it talks about producing hydrogen which has high energy content and its clean nature, meaning that it doesn't contribute to any CO2 emission to the atmosphere. So with this mindset, I already discussed that. Now talking about the process. So we talk about photoelectrochemical water splitting, which is basically the decomposition of water. So water, can be decomposed into oxygen and hydrogen, as we all know. The basic electrolysis, a breakdown of the water. But now, as we know, this water splitting is basically an energy-driven process. So it requires some kind of energy, and it is a kind of endothermic reaction, which needs energy to, get decomposed. So we have various energies like photo energy, we have electrical energy, thermal, and biochemical. So as we know, like we studied in electrolysis, we need some electrical energy to split water, right? So with that understanding, now here's a new process where we have integrated nanomaterials which participate as an electrode and use photonic energy to excite. So what happens as a process demonstration? Now, this is the photoanode that we have designed, which is a nanoengineered material. When we shine light onto it, like photons, basically, it get energized. And when it get energized, it produce charge carriers. So we have, the electrons which get excited from the valence band to conduction band, creating holes at the valence bands. So the holes at the valence band of this material, they participate in water decomposition. So water gets split into oxygen and H plus ions. So now we have oxygen produced at the electrode. However, we have H plus ions which are in the electrolyte now. So these H plus ions which are positively charged are attracted by the electron-rich counter electrode. And when these are attracted, like electrons plus these H plus ions produce hydrogen. So this is the beauty of this process, that it does not require any carbon precursors. It does not require any complicated processes. It just need a nanomaterial which is functional, which is highly, I would say, photoactive, and is capable of harvesting solar energy, like starting from UV to IR range. So UV, visible, and IR. So that's what is the focus of the project. We design materials which has their absorption spectrum in UV, vis, and IR. So now talking about a few research trends and methods for green hydrogen production. So as I mentioned that this process can largely contribute to green hydrogen production. So this is the I would say the timeline of this process. So it was first investigated by Honda and Fujima scientists in 1972. And since then, various researchers have made diverse compositions, diverse contributions to synthesize nanomaterials and, tune their properties for, I would say, highly efficient solar energy harvesting and further conversion to hydrogen as a clean fuel. So with this dimension and key timeline, we need to understand what are the challenges in this field. So when I mentioned, there have been some work related to solar energy harvesting and its conversion to hydrogen. So there is an efficiency. So that is solar to hydrogen, STH efficiency. So the maximum efficiency that has been reached so far is more than 8%. So that is around, I would say, 10% of efficiency is the maximum achieved by this process. So we see that there's a huge gap. So we need contributions by various material scientists and engineers, which can largely contribute with their knowledge in working with nanomaterials to design materials which can increase this efficiency. So the total efficiency of the process to date is only 10%. And the maximum photocurrent which is produced by materials is around 25 milliampere per centimeter square. So you see, it is still at a nascent stage, and more contributions can, lead to high advancements in this field. If you talk about fabrication methods that are being used to design these electrodes, so we see large contributions coming from vapor deposition methods or molecular beam epitaxy, which is used to make these electrodes. So again, we need diverse processes which can come up with highly engineered design of these electrodes. Another challenge that exists in this field is the stability. So when we talk about an electrode which has to participate in this reaction, so we need to consider the stability in aqueous medium. So we need an electrode which does not corrode, which is stable in aqueous media like water, seawater, or even acidic water. So the maximum stability achieved so far is like 5 hours. So we need to work on materials which are highly stable and contribute to material design. So these are few challenges and opportunities highlighted for our audience. So based on that, there are various research foundations that exist in this field, talking in terms of the research gaps and novelty. And we also talk about the choice of materials that one can choose for, while they start working in this field. So we see the complete, I would say, the family of elements we have in the periodic table. So one can, choose materials, design materials, and, start the synthesis to have an efficient electrode for this material. So basically, when we talk about how to design an electrode, we talk about basic properties, like we need to understand the band gap, we need to tune the photon absorption, we need to talk about stability, plentifulness, and also non-toxicity of the materials. Because here, when we work in green hydrogen, we talk about sustainability. So we need to choose materials which are eco-friendly, which are abundant, and which can be, commercialized. So we need to look into all that aspects. We also need to talk about the band edge potentials for water splitting, because when we need to choose a material, it should have their, conduction band edge and the valence band edge aligning or straddling across the redox potentials of water. So this is like more engineering perspective information. And the other thing is briefly highlighting our contributions to solar to hydrogen conversion efficiency. So we have few published reports which talks about the challenges, which talks about new research highlights and electrodes that we have, contributed to this field. So before, I won't discuss everything, but I have a strategy that I would like to share with the audience. So this is a recent work that we did, and we designed a polymer-based paper electrode, which was the first paper electrode, demonstrated for this field. So as you see, like we have a normal filter paper, which is a Wattman filter paper. So we decorated the paper with a conducting and I would say light sensitive polymer. So with this addition to the paper, we were able to demonstrate the paper for green hydrogen. So it's a short clip on my screen. I hope it's visible. So it's we also designed and filed patent for this work, which talks about designing a portable photoelectrochemical device to produce hydrogen. So with this response, we also see that it's highly sensitive to light. We have on and off response, which is like around 100 second, as a step size. So we see this is a lab device which is a solar simulator. So we mimic solar light with a solar simulator. We excite our material, and this is the electrochemical setup that we have in the lab. So you see, right, this is the hydrogen that is being produced with the effect of photons that we provided to the material. So we see this bubbles here. So this is basically the green hydrogen which is being produced. So further to this cell, we have a gas collection system which helps us to store this gas, quantify the gas. And similarly, when I talk about photoelectrochemical water spreading, so we know we design materials which are active in UV, visible, and even IR. So here are a few studies which we do in different monochromatic lights to understand the behavior of material in different wavelengths of light. So this again has so similarly here you see this is the photoelectrode which is kept here, and here is the hydrogen being produced. So a few videos just to give you an insight about the lab work that we have been doing. So now jumping from the research to the market potential and applications. So as I focused on sustainable energy as hydrogen, so we need to understand the competitive of hydrogen with other fuels. So if we talk about the energy density, that is the main factor. So it's about 142 kilojoule per kg for hydrogen. However, it's about half or even less than half for the other fuels like CNG, gasoline, or diesel. If you talk about fuel efficiency, so it's about 60% for hydrogen, and it's around 22% for gasoline and 45% for the diesel. So we see, right, the metrics are highly competitive, and the market is ready to invest in hydrogen, but it's just the efficiency of the process which is a hurdle today. But definitely with more growing research and trust, people will soon come up with electrodes which are highly efficient. So with this, we look into the era of green hydrogen beacon. So the key highlights, if we talk about the market potentials, so it is believed that by 2050, we will be able to bring down the cost of hydrogen production to 0.8 to $1.3 per kg. So that is a good paramount that we have in this field. But let's see how things go up and how eventually we accept green hydrogen as a clean energy fuel. So that's the one challenge which exists in the field. So with this, we also have a challenge that people often ask, what about storage of hydrogen? Because it's very important to understand, and it's a difficulty basically. So to just have few highlights. Basically, I don't work on storage technologies. My main focus area is to produce green hydrogen. So with that, we have collaborators which are largely contributing to storage. So we have nanomaterials like metal hydrides. We have carbon nanostructures like graphene, and even other carbon composites which are helping us to compress hydrogen and store with high storage density, and make light materials, and have various reactions to store green hydrogen. So with these advancements that are taking place in terms of storage, we really have to look forward to the integrated energy system for the future. So this is basically an overlook of the green hydrogen, which is a new energy accelerator. So starting from its production by various energies, like as I focused on solar energy being the prime energy, we can also produce green hydrogen by wind energy or other renewable energy sources. So with all these, we see the map which talks about its distribution, which talks about its hydrogen fueling station, because we need to talk about having more fuel cell based EVs. So with all that, we need a fueling station for hydrogen, the tube trailers, which carry hydrogen from the production station to distribution areas. So this is like a general, like an overlook of how an integrated technology of future might look like. So with this, if we talk about industrial beneficiaries, starting from Indian market to international, so we have abundant need for hydrogen. So with that, the more contributions to hydrogen market will definitely lead to high profits in terms of industrial beneficiaries. So the major one is Reliance in India, which is largely looking forward to have a great production of green hydrogen. So let's see how far we can get there. And talking about key challenges, so yes, there are many challenges because technology scale up is the major challenge. So when we talk about having hydrogen in transportation sector, in portable electronics, so we need to look into how we can engineer and redesign the automobiles and transports. So we need to talk about having fuel cell provision. We need to find solutions how we can change the regular ignition or combustion based engines to fuel cell based EVs. So all that has to be redesigned, and industry is having a large contribution to make in this green hydrogen change. But let's see how things go up. But definitely, we will be having green hydrogen as a primary energy carrier to cater our energy needs of future. So let's with that. I would like to jump into the other part of my presentation, which is on smart sensing. So with the previous part of my presentation, I talked about more, functionalized or energy materials. Now that I'll talk about few materials which are used for smart sensing. So as we know, we have diverse nanomaterials based on their design and their properties. We can use them for diverse applications. So when we talk about nanomaterial based sensors, we talk about their tunable properties, how sensitive they are towards any stimuli. So that's main thing that we need to understand. So with this, digging more and just understanding the design of a nanomaterial based sensor. So we have nanomaterial and we know they've been the beautiful properties in terms of their high surface to volume ratio. We understand their methods by which we can functionalize these materials to have dedicated a specific functional operation. For example, we talk about biomarker, we talk about cancer therapy. So we need to modify materials with specific markers that go and perform a specific application. So with all that, it's an easy task to basically functionalize the nanomaterials. We talk about their highly sensitive and selective response to processes, which depends upon the tuning of or the tunable properties of materials. So that's one aspect. So using nanomaterial as a base, we need to find recognition elements that are basically decorated onto nanomaterials to perform a specific task. So we talk about recognition elements which enhance the selectivity and is useful for a dedicated operation. Then we have a signal transduction. So basically, it can be an optical signal, it can be an electrochemical signal, or it can be any colorimetric or any other kind of transduction that is possible in the system. So basically, in my presentation, I'll be talking about more colorimetric. We talk about optical, and we also talk about electrochemical response that we have established for designing few sensors for water quality monitoring. So with this, we need to understand, like when we are designing nanosensors, what are we trying to do with them? So what is the figure of merit for, a good nanosensor? So when we talk about a nanomaterial, which is acting as a good sensing platform, so we generally talk about the limit of detection, like what is the lowest limit of detection that a material can, detect, that can find the analyte basically at to what level. We talk about limit of quantification, which talks about is basically what is the quantity, maximum quantity, or the lowest quantity that can be detected by the probe. We talk about relative standard deviation. What is the deviation in terms of sensitivity of the material? We talk about the precision and the accuracy of the response that is shown by the nanomaterial. So based on these figures of merit, we define the efficiency of a nanomaterial, and basically highlighting few of our research contributions to water quality monitoring. So based on my work, we have designed materials for water quality monitoring in terms of detecting heavy metals in water. So the main focus when I was in India, we were working on like basically as I come from North India. So we have Punjab, which has highly like water which is polluted with arsenic. So our major focus was closely working with the government to uh, synthesize or to engineer nanomaterials for detecting arsenic in water. So we had designed nanomaterials based on carbon quantum dots decorated with functional recognition elements for captivating this arsenic in water. So we were able to uh, analyze arsenic to the lowest limit of detection to 0.086 ppb. So that was a very low limit that was performed by the sensor, which was good enough to being competitive to other nanomaterials which have been reported. We also designed a probe which was used for the detection of selenium in water. So another emerging heavy metal and a water pollutant is selenium in the North India. So this was again a project in which we were working closely with the government to uh, detect selenium in water, basically the Punjab and Haryana water. So we designed 2 to 3 different probes for selenium detection based on the nanomaterial that we used. And we also have a probe that we designed for iron detection in water. So based on the way we functionalize these materials for dedicated heavy metal, so we end up with the specific selective response towards a heavy metal. So with this, for the iron, we were able to reach about 19.8 ppb was the lowest detection limit. So, moving ahead, we have chemical sensors that we designed for other materials. So, the first one is we talked about copper detection. We talk about again detecting selenium, but with an electrochemical response. So, the previous technologies of the chemical sensors that I highlighted were based on the optical response of the material, meaning it has an optical response in some wavelength. So when analyte is added, it shows an on and off as a switch, basically. So when an analyte is added, it gets off. So that is basically an on and off mechanism that is basically used for designing these kind of nanomaterial based sensors. So similarly, when you see a drift, a sweep in the electrical current, so based on the like electrochemical response of the material, so that is again we talk about electrochemical sensors for selenium detection. Similarly, we had some other green routes by which we were making these nanomaterials. So we used carica papaya waste pulp for synthesizing zero-dimensional nanostructures, that is carbon quantum dots, and further functionalizing them with a ligand, which was like EDTA in this paper, which was used for, basically detecting chromium in water. So another heavy metal which is quite famous in North India is the chromium. So we designed a probe for chromium detection. So based on this, we had various like reviews which are published in terms of the impact of heavy metals in water, and also the optical nanosensor based chemo probes that can be designed for detecting these materials. So with all these contributions, we also had few device development and technology readiness devices which were ready for the market transfer. So as I did my PhD in a national lab, so the best explored area was to have active participation in device development, because as a researcher we can not just think of doing research in lab. So it's basically lab to market understanding that one needs to progress to. So with that we developed devices. So this was one device which was used for a fluorimetric detection of selenium in water, which was based on the chemical probe that we made using a nanomaterial. So the other device we had is for the colorimetric detection of arsenic in water. So again, we used our material and integrated into a device which can sense arsenic in water with a colorimetric response. So again, this was some device development work that we did. So with this, I'm coming to the end of my presentation where I talk about the the opportunities which are emerging with the field of nanoengineering. So basically, the concluding remarks would be like, nanotechnology is growing up. So we need a large contribution, large interest from young students to contribute to this field and understand like the wide spectrum of applications of nano engineering. So when we do engineering, we do electrical engineering, electronic engineering, and even computer science engineering. So with all these disciplines, now when we try to make a nanomaterial functional for various applications at a nanoscale, so that is basically nanoengineering. So you tune the properties of material and find the suitable applications for sustainability of the planet. So with all these, there are different federal governments who are contributing energy, which are the main key players in accepting nanoengineering. So we see their interest growing up with the time. So there are many future developments which are existing in this field and will are realizable basically. So it is doable. So it's just like what spark we can create in terms of nanotechnology. So with this, I'll be happy to discuss more if anyone has any questions. And also, if we talk about science promotion and communication, which is a part which I'm closely related to. So with this knowledge which I have shared with you, so it is basically science promotion and communication. So I would request you all to further share these findings, share this knowledge that you have gained with other people, such that we can spark that interest in young generation. So that's what the goal is of talking to people, participating in these active webinars, and also to appreciate the contributions taken by the organizations to conduct these webinars. So I really acknowledge Dr. Shri, Dr. Bala, which has been kind enough to invite me to this platform and share my knowledge. So with this, I acknowledge everyone and appreciate everyone for their dedication and work that they are doing, and would like everyone to contribute to this field as a whole. So with this, thank you, and I'm open to any questions. If you have any questions, you can even write to me on my email. So thank you so much.
Thank you, Dr. Anupma. Can you explain these artworks which you do? Because I love art and I follow your work. Can you
Yeah,
explain?
so
Yeah, please.
yes, definitely. So, as a part of science communication, when we talk about nanomaterials, so to make them understand to young generation like students and kids, so we color these nanomaterials. So these are all nanomaterials, basically at the micron, submicron size. So these are Maximes, the latest materials that I'm working on. So we take a SEM image of this, basically a scanning electron microscope image of these materials, and then color them to find some art in them. For example, this is a Maxine Yoshi. So it is from a Super Mario game. So just colored this. This is basically a nanomaterial, Maxine, which is colored in a form that it represents some sculpture which can be relatable to students. So that's one thing. Then we have this Dory, a fish, which was a nanomaterial, which was morely closely related to a fish. So we just colored it in the form of fish to get attention. Then this was a dragon, exactly not a dragon, basically a Maxine flake, which was sitting on another flake but looked like more like a dragon. So we just used uh, Photoshop to color them and make them more, reader friendly, or I would say student catchy.
Yes,
So
yes. Very
yeah.
attractive because I was really impressed when all these artworks of yours are winners at all these science, art, spring, fall, and everywhere you go, you always put up in your Twitter that I feel very happy because this is how, as you correctly said, engage the young children and young students into the science. That is what attracts them when they are kids, right?
Yes, yes, that's what, to spark interest in nanomaterials. So these are like small steps that each one of us can take, to have more participation. So this is what, like, as a young faculty, young researchers, we all can contribute to. So
You are
that's
all
what.
young. We are not young anymore. That's why we rely on you to take this baton forward because at least I think I'm old enough to rely on youngsters like you. And
No, but
correctly
you're really
said,
doing great as a woman scientist. So I
Yeah,
really, get inspired by you as well. So
yeah.
it's collective efforts by each one of us
Definitely,
contributing to this
definitely.
field.
Especially STEM education requires women scientists. Definitely, we need to do a lot. And I'm really inspired by your previous picture. Can you show it once again? Where all the pictures, the previous slide, where you
Uh-huh.
have shown all the women students in that picture. Yeah, this one.
Yeah.
Yes,
Yeah,
yes,
these are few pictures that,
yes,
as I mentioned, like when I was in India, we used to go to schools every weekend. Like that's what, like we used to contribute to large
yes. We also go
science
and
communication.
yes,
So,
very, very important work we have to do because as scientists, we are role models for them. Once we go and
yes.
talk about our profession, our job, the work, the research we do, they really get excited and inspired to see that this is an option for them too.
Yes, definitely. So we need to provide that platform to, young students. So that's all we all can contribute to.
Yes, thank you so much. And with that, I definitely request the audience to interact. And I request if all the audience, because we are very limited numbers, we can switch on our video mode. And Dr. Kannan has joined us. Dr.
Mhm.
Kannan is the director of Global Biomedical Research Foundation. So Kairos Kinetic and GBRF together we host this weekly Thursday webinar series. And as you correctly said, our intention is to do this knowledge transfer, invite all the researchers and scientists like you who can share their current work because by the time we read a journal article, it's already 2 years old. The work is
Yeah.
already peer reviewed multiple times, and by the time it gets published, it's taking time. But when we invite like this, you share your current work. That is why we thought we have to do this weekly series. And Dr. Bala is our trusted mentor, and he invites through his 3 decades of experience globally. He invites all the uh, experts, and Dr. Kannan and Dr. Bala are friends from school, and that's how both of them are my mentors and guides. Now, I would definitely invite the participants to interact with you, but I do have a bunch of questions because I have been reading about the sustainable planet and global warming, and recently I started book on A Planet to Win, and that's where I was reading. Your topic was also very fitting into that. So since I got your title, I was reading extensively so that I can, relate to the topic and ask you some smart questions. Dr.
Mhm.
Anupma, when you say the first half of your presentation was heavily into a very interesting angle, how you are contributing to stop our planet not going to this crisis, and you specifically mentioned about carbon dioxide emissions, carbon dioxide
Yeah.
capture, and all that. So, with that thing, are we on the track to stop this 1.5 degrees Celsius rise in the temperature? Or are we really going to achieve it by 2030 or 2040 with the current efforts?
Yes, definitely. That's what, like, we need alternate energy fuels which can stop the CO2 emission into the environment. So, with green hydrogen, with sustainable renewable energy like solar panels, definitely we will be able to, reduce that global warming. So,
But
that's what is thought of.
yes, but when I read this
Mhm.
POC, that is Alexandria Ocasio-Cortez and other US Senate members, Green New Deal, and the
Yeah.
kind of recommendations they made in US, we are not seeing that kind of approach in India, such a
Mhm.
stringent and activist oriented approach for doing the same thing in Indian politics. So because you are in US but you come from India and we are in India and we are looking towards US and other parts of the globe to attract this attention for climate crisis. So what do you think, like because global south is heavily affected right now with this kind of severe drought, severe heat, and we are entering into summer in India right now, and it's already heated up in Chennai at least. So with this kind, because I'm very happy that all of you are working with these solutions, but they're not getting even solar. We are listening for so much, but it's not scaled up right now. Even in Chennai, it's not on my terrace. We are a gated community. It's not on our terrace, but it is deployed in minuscule measures. It
Yeah.
is not widespread. The
Mhm.
technology solution is there, but it is not deployed widespread. So with that
Yeah.
kind of gap, I want to be hopeful, and I want to realize that all of our solutions will be able to protect our planet. But coming to your green hydrogen concept, you're all working that, but do you think India is also making such efforts to because we see that we also have a mandate, because my husband works in Indian Oil Corporation and he's a
Yeah.
metallurgical engineer, and they also have a mandate to reduce these emissions and all that. So when is this green hydrogen concept going to be widely scalable in India?
Yeah, so if you look into the numbers, so we already have ISRO, which has already you established the green hydrogen-based fuel cell bus, so which is running in Bangalore. Like, so we have different like Kerala. If you look into Kerala hydrogen energy map, so they have few trial runs going on the fuel cell based on hydrogen. Local buses which are on trial runs. If you talk about Delhi, so Delhi again has 5 buses running on hydrogen, which is fuel cell based buses. So few trials are already in like progress in India. And also, if you talk about, you mentioned about what industry can largely and government can contribute. So I would say the G20 mission of Indian government is also having a strong sphere of sustainable energy. So under those sustainable energy, the focal point is green hydrogen. So Prime Minister Modi is also getting involved largely into, I would say, participating in green hydrogen economy. So with his words, he has promised, like, in a decade, we think we can have $1 cost of 1 kg of hydrogen. So that means if you have 1 kg of hydrogen as a fuel in a vehicle, the energy density of hydrogen is high. So you 1 kg can last about a longer run for the vehicle. So that's what we are aiming, and largely I believe Reliance also has this mission, large contribution to green economy. But as we say, like, we are a country with huge population. So to understand that, the changes might look small at the moment, but definitely we have larger goals. So let's hope for the best. As you mentioned, like, we are hopeful, and engineers like me and you, so we all can just be hopeful.
Definitely, definitely. I definitely want to be positive, because that is the only way to go forward. And coming
Yeah.
to your last part of the presentation, where you talked about biomedical applications, especially with your water quality surveillance, especially with
Uh,
heavy metals. Do you have any future plans to come into this, as you correctly said, about this cancer research or biomedical research with your nano applications? Because
yeah.
cancer
So
is one of the top list for mortality and morbidity in India right now.
yeah. So if you talk about, like, as I said, like, I'm basically a nanotechnologist, but definitely we have collaborative groups which are specialized in biomedical research. So
Mhm.
what we do is we engineer materials based on their demands. For
Mhm.
example, you need a material which has high optical response and has few kind of selective functionalities. So we engineer materials for them. For example, recently we are working with a school of medicine in US, which is basically trying to have materials with high photothermal response to design some kind of photothermal therapy for cancer treatment, say,
Mhm.
for other treatment, for antibacterial, antimicrobial treatments and all. So that's what, like, we basically, as an engineer, nano engineers, we design materials for specific properties.
Okay.
So, but definitely, as you say, like, like, I'm open for collaborations in that aspect. But
Yes.
definitely, like, for now, like, I still
You're
as an
focused on
independent
industry.
researcher.
Yes.
Yeah,
Yes. Yes.
it's still
Great.
difficult, but definitely, let's see how it goes.
Yes, definitely. I totally understand. Everyone has their priority of interest areas in research, but it is
Yeah.
really exciting. Your presentation, unlike every other presentation in our series from November, we are conducting this every Thursday, almost, except for 1 or 2 weekends when festivals coincided. But this is the most exciting in the current times, because the entire world is really worried about the entire climate crisis. It's almost like an existential threat for the future generations, and your presentation has actually wide opened our understanding how much research is happening in this particular area with the green technologies and all this. And I'm really hopeful that down the time, like another 5 or 6 months later, you would be able to come and share much more information with us, so that we will be updating ourselves. And are you attending any G20 summit sessions or anything like that?
Not really from here, but basically virtual was not allowed. So, but
Okay.
definitely, like, I look back to come to India and join as faculty soon. So let's
Okay.
see how it goes.
Oh, great. Then we would like to see you, India, once you complete your studies there. Then
Yeah,
try to catch up. Thank you so
Yes.
much for taking time so early in the morning. And
Mm.
I'll keep in touch with you in Twitter and follow your work. Yes,
Yes, thank you for inviting me. It's the best thing. Like, I really love to do science communication
I
and
know.
talk about the ongoing research that we are doing, because this is very important to motivate others. So with this
I'm
perspective, I
motivated with
acknowledge
your
you.
work.
Yeah, so
Your
I
work is so motivating.
acknowledge, yeah, I acknowledge everyone. And this is a great platform, I would say, conducting webinars and talking to researchers and giving them platform to share their knowledge. So I really appreciate and, thank to all of you. So thank you so much.
Have a great day. And
Yes.
with
Have a
this,
good time.
I thank all the participants for attending today's webinar, and we hope to catch you next week with another speaker. Have a great evening. Thank you all.
Yes. Thank you.